All right, how's everybody doing? Are, yeah, are your brains full yet? That's a lot of content for one day. So my name is Paul, and I've got some good news, and I've got some bad news. The good news is we are 3 sessions away from the Optane giveaway, and even more important than that, then the bar opens then. The bad news is 2 of those sessions are mine, so you get to listen to me. You get to listen to me twice. And I'm going to challenge the cameramen because I can't see these little miniature screens here, so I'm going to be all over the place. And I know the lighting doesn't work that well down here, but I look much better in dim light anyway. All right, so I'm Paul. I'm going to talk about, okay, I thought I was doing my other talk now. So I'm going to talk about SPDK and PMDK. So we've talked a lot about persistent memory really over the last year, and there were a lot of questions about it today. So we've got a couple of kits, and Jennifer even mentioned I guess 4 of them this morning. One of them is PMDK, and of course the other one is what we're doing now with SPDK. So I'm going to sort of compare and contrast the two and talk about a couple of different ways that we can integrate the two. One way which is already done, and then a couple other different ways that we've thought about, and there's even more than that. Okay, so if I do my job right here for the next 30 minutes, you're going to at least walk away, if you don't already have an understanding of the SNIA NVM programming model. That is critical for understanding persistent memory. The whole PMDK is really based on that model and everything that was discussed as part of that twig that's been around for, I don't even know, 4 or 5 years now. You'll learn a little bit about PMDK in the overview. I'm not going to go into a lot of detail, right? They actually have their own set of sessions that they do at the NVM Summit every year. But you're going to get a preview of what that is. Got a couple of slides that talk about the comparison of the two. Again, not a great amount of detail, but enough that you hopefully will walk away and go, okay, now I know a little bit more about how these two fit together and more importantly, how they're different. All right, and then of course we'll talk about the integration that I mentioned and some potential use cases. All right, so this slide's been around for at least 4 years. And I think it's been drawn exactly like this the entire time. It was actually drawn on a napkin by Andy Rudolph on an airplane, just for a little bit of trivia. I'm not going to go through all of this because it's not really relevant to what we do with SPDK. Everything on the left-hand side, all this stuff, is really either management or block-oriented. And you might say, well, SPDK is all block-oriented, so why aren't we going to talk about that? That's SNIA programming model block stuff. Right, what we're really interested in when we talk about the integration of the two is direct access mode, and that's the stuff on the right-hand side. And you'll see, if you're not already familiar with this programming model, there's a control path and a data path. And although persistent memory and everything about PMDK is just like SPDK in terms of user space, direct access, and in this case, really direct access. I mean, you're talking directly to the media, to the persistent media, when you're going down the data path. As this programming model was developed and understood, right, a lot of questions came to mind about security, about organization, about hierarchy, and how are we going to manage all this stuff? And sort of a light bulb just kind of went off and went, you know what? There are things called file systems that people have been working on for a very long time that already solve a lot of those problems. So persistent memory in the SNIA programming model takes advantage, a significant advantage of all of the features and capabilities of file systems. For securities and hierarchy, all that kind of stuff, which is why if you're going to use persistent memory with the SNIA programming model, you have to have a persistent memory-aware file system. You have to have a persistent memory-aware kernel. And today, and I don't have the list of them, but it's all in Linux. NTFS is persistent memory-aware, starting with, I forget, 2016, I think, server. But all that stuff is persistent memory-aware. And really, the fundamental concept is pretty simple. If you want to treat your storage as memory, byte-addressable, non-volatile memory, you just do a file mapping. You do a file mapping, and if you've got all the right stuff in place, as soon as you operate on that, as soon as you do your loads and stores, and make a few extra calls to deal with persistence, it's done. And you might wonder what those few extra calls are for, and it's simply because persistent memory sits at the end of DDR, and obviously, until persistent memory, there's never really a reason to flush things all the way to DDR. Because if you lose power, you lose it anyway, right? So a lot of what persistent memory, some of the challenges for application developers has to do with making it persistent, dealing with all of these buffers and caches and everything that sit between host memory and the tail end of where the media is off DDR, making sure all that's persistent. Okay, so the PMDK. Key thing here is the website's pmm.io, just like spdk.io. There's tons of great information out there. There's lots of blogs. It's a fully open source project. Also, like SPDK, it's not like one thing. Okay, it's a series of libraries, and I'll talk about a couple of those libraries coming up here on the next slide. It's fully validated. It's fully performance tuned, 100% open source. Contributors from HP, from Intel, from all sorts of different companies. It's not the only library of choice for persistent memory programming, but it's got some significant popularity. Okay, so lots of stuff on here. Like I said, PMDK is a collection of libraries, just like SPDK is a collection of libraries and applications and frameworks. And they all do different things. And I'm not going to go through each and every one of these because, well, just simply because of time. But really, one of the key ones here is this one right here. It's called libpmem. And as I mentioned earlier, one of the challenges in making your persistent memory persistent is understanding what you have to do based on not only the processor, but the version of the processor that you've got in terms of flushing all the different caches and the different buffers. So this base library here actually does all of that for you. It's got some very simple functions that you build in your application, and you can just say, make persistent, and you give it the name of the handle of the file mapping that you want to make persistent. It figures out the best way to do it and does it for you. And actually, depending on which processor you've got, it can actually be a completely different series of steps. So that's kind of an important one. These other ones all do different sort of value-added things. They all build on libpmem. I actually pointed at the wrong one. There's libpmem. But all these other things build on top of it. As an example, libpmem.obj deals with objects and making objects persistent. And there's a lot of transaction support in here as well. And we probably got a lot of file system people in here. If you're an application developer traditionally and you haven't dealt with writing a file system or dealing in low-level storage, you're not used to transactions and atomicity and having to deal with rolling things back and what do I do if I'm halfway through something and it doesn't finish? If you're an application developer, you leave that to the storage people. Well, with persistent memory, these are problems that you have to solve yourself, right? Because if you even just do an allocation of persistent memory and lose power, what are you going to do, right? There's nothing underneath you. It's you and the media. So these libraries are all really cleverly crafted to handle those problems for you. And in fact, the transaction support, which I don't have an example in here, but you can go up and find it on pmm.io, is actually macro-based. So you can wrap a series of read and write operations with macros saying this is a transaction. And the library itself will handle rolling that back if it doesn't complete before the end of your last macro statement. So there's some pretty cool stuff. It would be challenging to write to persistent memory without these helper libraries, for sure. And you can see different language support for libpmem.obj. Libpmem block, I'll talk about that on an integration slide here coming up, because that's where you may have seen that in the SPDK repository implemented as a BDEV module. And we'll talk more about BDEV modules in 45 minutes or whenever I'm up here next. All right, so comparing PMDK and SPDK at all sorts of different levels, just trying to frame them in your head. When would I use these? What do they do? How are they different? A lot of these terms are overloaded, and sometimes you say SPDK's programming model and PMDK's programming model, and they can mean different things to different people. So this is by no means an exhaustive list, but is an attempt to, again, just sort of provide the frame. So I/O model with PMDK is absolutely synchronous, right? You're dealing with the fastest media on the planet directly. When you do your loads and stores, you are talking to media. You don't have anything in between, right? So there's absolutely no reason to wait on a load or a store. You do it, you're done, and you're finished. And again, there's that persistence call I mentioned, but other than that, it's synchronous because the media is as fast as it gets. SPDK, as everybody is well aware, asynchronous, right? Because even with the fastest media we've got today, it still makes more sense to get your I/O submitted and get a callback when it's completed so you can get more work done. So primarily asynchronous for SPDK and primarily synchronous for PMDK. Whether your application has to change or not, actually I could have probably said sometimes for both of them, but if you do PMDK the right way, meaning the most efficient way, that path that I showed you on the right-hand side where you're changing your application dramatically and actually allocating your data structures in persistent memory, then you've got a lot of work to do. And that's why the libraries were written to try and minimize that. But just think about that for a minute. You're no longer doing IOs. You're not saying, I've got this data, I'm going to package it up, I'm going to ship it down the wire. You've got a C structure, and you just want to allocate it in persistent memory. That's a pretty drastic change in how you think about what the code is that you're writing and how it works and what it does. Data access granularity, and this is kind of sort of a given, I guess, because most of the time we talk about persistent memory, we say byte addressable, non-volatile memory. There you go, it's byte addressable, right? So you don't need to live within the confines of a block. If your application needs to deal with a cache line, you don't have to read an entire block, modify it, and write an entire block back out. You modify that cache line in place, and it's done. So it's all byte granularity. And of course, SPDK is block-based. Data access style, kind of already touched on this, and we'll do a super simple short example on the next slide. With PMDK, it's memory, right? It's persistent memory, so you access it like you do memory. You dereference pointers, you update locations, you do all that kind of stuff. With SPDK, we're, of course, I/O-based, right? It's an I/O model. I'm going to build an I/O, I'm going to ship it off to whatever the abstraction layer that I'm at, and I'm going to get a completion back. Media, PMDK, deals pretty much exclusively with persistent memory. And as you are all fairly well aware, SPDK has all sorts of different things that it can talk to, right? Whether it's an SSD, or whether it's persistent memory with the integration that we'll talk about here in a second, or AIO, just all sorts of stuff. Really anything can live behind the block device abstraction layer, and you can talk to it like a block device. And then they're both open source, which is hugely important. Okay, super simple example just to help you put together the pieces that I just went through. So let's say I want to do a write operation. I think I chose write. Yep, let's say I want to do a write operation to my non-volatile memory. So in persistent memory, it'd be to my PMM, and in SPDK, it'd be to an SSD or something. Let's go down the PMDK side first. I do have to integrate libpmem at a minimum with my application just to make it easy to allocate persistent memory in an atomic way and to make persistence in an easy way. Those other libraries all do other really cool things. I could do those as well, but just for a simple write, we just say, okay, I need libpmem. I'm now going to memory map my persistent memory file in my persistent memory file system with my persistent memory aware OS. And the actual name of that API is pmem map file, right? Not pretty intuitive. And then I can perform assignments directly on those memory addresses, right? It's just in the same way that if you're an application developer, you've been doing for 20 years if you memory map files. It's just in this case, you don't have to flush and go through the kernel and go through the page cache and go through the I/O model and get everything down to the disk. You make that one call to persistence, and it's done. So that's what the next step is. And the actual name of the function in libpmem is pmem persist, right? And you're finished. In SPDK, of course, you integrate SPDK with the application if that's what you're doing. And as we all know, you can use pre-built applications in SPDK. You can use libraries, you can use the framework. However you do it, you've got an integration step. You're going to have to allocate a DMA safe buffer to do your IOs with so that obviously it's DMA safe when your controller does DMAs. Using a block layer device API, you'd make a call like SPDK bdev write, right? So this is, again, I/O model. You've built up an I/O, a bdev I/O. You've sent it in through the bdev layer with this API, and now somebody's polling for completion, right? And when it's complete, you're finished. So once that has been accepted by the NVM controller, right, and the memory is DMA'd back up and you get the completion, things are done. So you can see When we talk about programming model, I/O model, what's the difference between these two? It's pretty vastly different in how they operate. And again, I can't stress enough the more you can think about the idea of persistence around your structures as opposed to persistence around I/O, that's really the big shift in thinking when you start talking about persistent memory. Okay, so let's look at a couple of different integration options, and this is by no means an exhaustive list. These are just things that a couple of us had thought about, might be worth talking about, some more stuff we can talk about tomorrow at the developer meetup or over a couple cervezas here when the networking hour starts. In this case, what we're actually representing here is an application that's using both libraries independently. And I'm not saying this is the way to do it. None of these, I'm not saying any of these ways that we're going to talk about are the way to do it. It really depends. It depends on the makeup of your team, your development team. It depends on your application, the architecture of your application. It depends on your time frame, how much time you've got to do this. It depends on what you're trying to do with persistent memory. But an example like this says, for whatever reason, I don't want to mess with the SPDK side of my application. It does what I want it to do. It's production. It's perfect. I don't want to mess with it. I've got another use in my application for persistent memory. So why do I want to entangle these two kits? Well, you don't have to, right? They can work completely independently. So if you look down, right, this side, this is your SPDK side. You're talking to block devices because you've integrated SPDK in your application. It's lightning fast. You're going down through one of our pulled mode drivers. And then some other section of your application that may do something completely different, maybe it's cache, maybe it's whatever, has integrated PMDK, has done its control stuff through the file system, memory maps a file, starts operating on those memory locations, and persists the memory directly. So sort of integrated into the application, but not integrated into SPDK. Now, the potential use cases for all of these different sort of integration scenarios are all kind of the same, right? And if you go out and look at any of the videos from the PMM folks or look on pmm.io, you'll see things that are fairly intuitive, like cache, anything to do with metadata, right? Anything that you want to be super fast and take advantage of the properties of persistent memory, which I haven't really talked about, but right, they're a lot faster than SSDs, a little bit slower than DRAM, and the cost point is somewhere in between. I don't know. I'm an engineer, right? $1 million for a persistent memory stick. I don't know. But yeah, this would be one way you could do this. Now here's an integration option that actually exists today, right? So you can go up and see this. This is in the master branch. It's been around for, I don't know, a couple of releases. libpmmblock is this dude, and it's implemented as a BDEV module, as a base BDEV module, and I'll define those terms here in 45 minutes or so, so that we're all speaking the same language. But you might want to do this if the performance, once you've tested this, is good enough for what your application is, and you don't really want to change the semantics of anything in your application. You still want to talk blocks, and you're already user space, and you want to figure out how do I use persistent memory with the minimum amount of effort possible. Well, we've already integrated this thing, which, by the way, happens to be nearly identical to the kernel mode driver in Linux for persistent memory, the block-based kernel mode driver. And it has to do more than just typical block kind of stuff, because it has to now be responsible for the atomicity of a block as opposed to a cache line. And that's all done in software, at least with the hardware solutions I'm aware of. So that's all part of what this does. So it basically talks BDEV out the top, does all the magic with libpmm and libpmmblock, and talks to the persistent media in the same way that you would if you were doing byte access, right? So it's doing all that for you. So it's basically a translator, right, between block and persistent memory. And again, same kind of use cases. Maybe it's a stepping stone for your development team to get to persistent memory through the NVM SNE programming model, which technically this is still the programming model right here, but it's not up here, right? Your application isn't using the programming model directly. So you might be leaving a little latency on the table doing this, but if it's good enough, then it's good enough. And now let's say you want to do super tight integration, right? You want your SPDK application to be completely aware of what it's doing, why it's doing it, and make it as just fast as humanly possible. So in this case, you want your BDevs, your modules, you want them to actually access persistent memory as memory, right? And you don't want that block abstraction. This would be, obviously a little bit more work to do this, because now you're integrating both SPDK and PMDK in the application and in SPDK. So there's some work in the community to get this done as well. But you can think about some of the use cases, same kind of things we mentioned earlier, and Jim just mentioned about potentially using an open channel, or you can even use this in NVMe over fabrics. Think about now your memory target isn't a memory buffer, it's the actual persistent memory. And there's no extra stuff going on in SPDK. You just talk right to the media, right? So this is probably about as optimal as you can get. And again, same kind of use cases: super fast path, metadata storage of any kind, write-ahead log, all that kind of good stuff. All right, so I think we've got a couple of minutes for questions. So any questions, PMDK, SPDK? All right, whoever's got the mic, there's hands.
Wow, the right side of the room's rocking it now. Left side, you better pick it up.
This is the persistent memory side.
Hey Paul, just trying to understand the PMDK flow. So in the control path, when we map the file, we are kind of giving the zero copy access, right, in a way. So when a read or a write happens, that's like a commit or a flush kind of an operation. Is that how I should interpret that?
Yeah, that's exactly correct. The only thing you have to do after you've done the file mapping is that, the example call that I mentioned called PMM persist, which is, a series of low-level CPU instructions to make sure those buffers are flushed. But after you have set up the file mapping, the kernel's out of the way, the OS is out of the way, everything's out of the way, you're talking directly to persistent memory.
Okay, I see. Okay.
Hello. So you have mentioned a couple of APIs like PMM map file and all that. So I'm just wondering, would they be standard across the OSs? Is there a plan to push them in POSIX or something like that? Is there a way to standardize it, or you're not there yet?
So it's crazy when I go over there. So the whole reason that this programming model exists under SNIA, and this twig was created, like I said, I forget, I don't know, 4 or 5 years ago, was to develop a programming model and not an API that would be pushed onto the OS vendors. So the OS vendors, all of them, including Microsoft from, I think, day 1 or day 2, were part of, and still are part of, this programming model twig, defining what are the semantics, what are the verbs for actually doing persistent memory. Now the implementation of those things is done the same, basically, in all the OSs. But when we talk about, for example, file mapping, the API is obviously different in Windows than it is in Linux, but they both follow the same semantics. So at the OS level, they're doing the same things, and they're trying to use legacy APIs, so that's where the standard part is. libpmm itself is an open source helper function library kind of thing. So the function call that I mentioned, pmm map file, is just a helper calling OS specific APIs that are required to map files that are going to be different per OS, but the same as what they used to be, or pretty darn close to the same as what they used to be before persistent memory. So I don't know if that sort of answers the question or not. But at the OS level, yeah, everything is standard and based on the SNIA programming model.
Saying that this is the sorry, is there when we use POSIX API, we know it's a POSIX, so we can rely on it. So now there's no such standard body which is endorsing your API or something. So is there any standard body which would be stamping the APIs?
So when you talk about the APIs, again, we have to separate the library APIs versus the OS APIs. So the OS APIs, the standard is the programming model from SNIA. So it's, again, more about the verbs than it is the APIs. And the OS vendors, the kernel guys in Linux and the kernel guys in Windows both follow the same programming model, and they use the APIs that are most adaptable to what their development audience has been used to using for the last 20, 30 years when we're dealing about the control path. So SNIA is the only standards body associated with this. And when Microsoft made the changes to, map view a file or whatever it is, I think that's what it's called, they obviously want to minimize the changes to that API versus legacy ones. And when the kernel guys in Linux made their changes, right, they wanted to minimize the changes to their API versus the Linux ones. So there's not a common API for dealing with persistent memory. There's a common programming model. And again, I mentioned there's more than just libpmem, or the PMEM libraries, the PMDK. There's at least 2 others that I can think of. I think HP's got one. And people are taking different approaches. Some people have built this into compilers. Some people have done, like what this open source project did with transactions and done a bunch of macro magic and some really cool stuff. But it's an open source project with helper function libraries built around the SNIA programming model, but you're not going to find an API that everyone's going to agree on is the right API to help with mapping persistent memory files.
Any other questions?
Good question, though. Thanks.
All right. Oh, we got one. Just made it. Just. Yeah.
So my question is,
Here, hold on. Here comes Seth.
He's got a mic.
so I've done just a tiny bit of work with PMDK. The package offers some options for emulating persistent memory on traditional I/O devices.
Right.
You don't recommend that anybody build on top of that layer.
No, I don't think anybody in that community would recommend that either. The reason for that might be obvious. It's because the software and the ecosystem and the programming model light years ahead of the availability of the actual hardware. So yeah, everything was emulated and talking to essentially RAM, so you get the programming model going. And I worked a little bit on the Windows side of it, helping the Microsoft guys get PMDK ported over to Windows. And it's the same thing there, right? Without hardware, you do the best you can. But yeah, I don't think anybody would see any benefit. In fact, you'd probably pay a penalty if you filed PMDK and had something other than persistent memory down there.
I tried standing up PMKV on memory mapped NVMe devices, and
Yeah.
that's not the best way to go.
Yeah, it's more of an enabling capability certainly than production. So, okay, so that's it. So thanks everybody. I'll see you in half an hour for the next thing.
Thanks, Paul. Good stuff.